Welcome to This Explainer. You know, if you've ever wondered how your phone just automatically translates a web page with, frankly, eerie accuracy, or how a chatbot actually understands the subtle context of that massive paragraph you just typed, you are in exactly the right place. Today, we're decoding the brains behind that operation. We're diving deep into topic 6.2.2, recurrent neural networks, and we're going to unpack the hidden math that makes these systems actually tick. Okay, so let's jump right in by asking a really fundamental question about how machines read. Think about the phrase, the dog bit the man, versus the man bit the dog. I mean, it's the exact same words, right? But the meaning is completely flipped. Older standard AI basically just looks at static snapshots of data. It's kind of like throwing a bunch of words into a bucket, giving it a shake, and hoping for the best. But human language just doesn't work like that. It needs order. Context is literally everything, and the order dictates that context. So here's our roadmap for today. We're going to cover 1. The sequence data problem, 2. Introducing RNNs, 3. How the network remembers, 4. The unfolding time flaw, 5. Fixing memory with gates, and finally 6. Seek-to-seek learning. Basically, we're taking a journey from a major roadblock in early AI all the way to the magic behind modern machine translation. Let's get right into it. Number 1, the sequence data problem. Let's start right at the foundation. What kind of data are we actually dealing with when we talk about text or speech? When we talk about sentences or speech, data scientists call these sequences. Now, mathematically speaking, a sequence is a matrix where each row is a feature vector, and, this is key, the order of those rows fundamentally matters. But, let's break that down into plain English. Think of a feature vector as a super detailed snapshot of info at one specific moment, like a single word inside a long sentence. String those snapshots together, and suddenly the data isn't just a static picture anymore. It's a story that unfolds over time, where chronological order is absolutely crucial to getting the whole picture. And this is exactly why early AI struggled so much. Standard feed-forward neural networks, well, they fail miserably at reading text because they completely lack loops. The data just moves one way, straight from input to output. Because there are no loops, there's absolutely zero capacity to carry information from the first word over to the fifth word. It literally forgets the beginning of the sentence before it even finishes reading it. So we needed a totally new architecture, the recurrent neural network, which is literally built with loops to handle sequence data natively. Moving to part 2, introducing recurrent neural networks. What's super interesting here is how this concept actually introduces memory to machines. The absolute game changer of the RNN is this concept of a state. Because these networks have those internal loops, every single unit inside the recurrent layer holds onto a real-valued mathematical vector, its state. Think of it as the network's short-term memory. It's kind of like keeping a running tally in your head while playing blackjack. When a new card drops, you don't start counting from scratch, right? You just adjust your current tally based on the new card. The state works exactly the same way, letting the network remember the previous step and merge that context directly into the current one. It fundamentally changes how machines experience the flow of time. When we unfold an RNN over time, we see exactly how it reads text just one feature vector at a time. The network doesn't just swallow a sentence whole in one giant gulp. It reads step by step, and crucially, it passes that hidden state, that running short-term memory, horizontally, right from one word to the next. Step 1 informs Step 2 informs Step 3, and so on. Number 3, how the network remembers. So what is the actual math happening inside this continuous memory loop? How does it blend the past and present without just getting totally confused? It's actually a really specific mathematical dance. Every single unit in the recurrent layer gets two inputs at the exact same time, the current word it's reading right now, and the state vector from the previous time step. It calculates a linear combination of these two inputs using learned weights, and then applies what's called a tanh activation function. Essentially, it's like making a continuous smoothie. You take yesterday's leftover blend, which is your previous state, throw in today's fresh fruit, your current word, and blend them together using that activation function to get a brand new flavor for the future. Section 4, the unfolding time flaw. Sounds perfectly elegant, right? Well, hold on. There is a massive complication when these networks try to read longer sequences of text. Here's what actually happens in the wild, and it's a super frustrating flaw. As a sequence gets longer, early feature vectors tend to be entirely forgotten. Imagine a paragraph starting with the really important pronoun she at step 1. By the time the AI reads through all the complex middle words and gets to step 10, where it needs to interpret the word her, the machine basically has severe amnesia. The memory of step 1 has been diluted and overwritten so many times that it's just gone. The crucial cause and effect link between distant words is completely broken. The technical term for this memory loss is the vanishing gradient problem. During the training phase, the algorithm uses something called backpropagation, which relies on the chain rule from calculus. And practically speaking, that means it multiplies lots of very, very small fractions together over and over. If you multiply 0.1 by 0.1 by 0.1, that number gets incredibly tiny, incredibly fast. In fact, if you do this across a sentence of just 20 words, the gradient practically hits absolute zero. The network goes completely blind to the start of its own sentence, preventing the earlier layers from training at all. Number 5. Fixing memory with gates. So if the network gets severe amnesia on long sentences, why does modern AI work so wonderfully? Well, researchers came up with an absolutely brilliant fix. Enter gated RNNs. Specifically, groundbreaking architectures like long short-term memory networks, LSTMs, and gated recurrent units, or GRUs. These models take a totally different approach. They borrow an idea straight from regular computers and store info like bits in physical memory. This was a massive paradigm shift. It literally upgraded AI from having goldfish memory to actual long-term reading comprehension. By acting like computer memory bits, they can actively decide to keep valuable info tucked away safely, specifically so they can pull it out to process related words near the very end of a long sentence. And the absolute craziest part? Human engineers didn't hard code these rules. These memory units use activation functions between 0 and 1 as a literal mathematical gates. They learn directly from the training data exactly when to read memory, when to write new info, and when to just erase stuff that isn't useful anymore. It is a fully dynamic, self-managing memory system adapting in real time. Under the hood, it's brilliantly simple. Take a minimal gated GRU. It has a mechanism called a forget gate. Think of this gate as a super strict bouncer at a nightclub. If the gate outputs a number close to 0, the bouncer keeps the door shut. The memory cell simply applies the identity function, meaning it keeps its exact previous value perfectly intact. But if the gate is close to 1, the door swings open and new info floods in, overriding the old. Because these gates can lock information in for a long time without multiplying it by tiny fractions over and over, the gradient doesn't vanish during training. Boom, amnesia problem definitively solved. Number 6, sequence-to-sequence learning. Okay, let's bring this all together and see how it builds into the real-world apps you interact with every single day. Sequence-to-sequence, or seek-to-seek learning, is this genius two-part system powered by those gated RNNs. First, an encoder network reads the sequential input and compresses the entire meaning into one single mathematical matrix, a numerical embedding. Imagine squishing a whole, complex English sentence into a dense diamond of mathematical meaning. Then a second network, the decoder, takes that dense diamond and carefully unwraps it, generating a brand new output sequence step by step. And this is exactly why this matters to you. Every single time you use a conversational interface or ask a smart assistant to summarize a massive document or flawlessly translate an email, you are watching this exact sequence-to-sequence gated memory architecture do its thing. The encoder reads the input, turns it into that universal numerical embedding, and the decoder unwraps it into a perfect new sequence. It's incredibly powerful tech operating right in your pocket. Which brings us to our final thought for this explainer. We've seen how gated memory solves the unfolding time flaw, letting machines actually master human language. But if an AI can be taught to perfectly remember the past, to accurately predict the future of a sentence, what other complex sequences in our universe is it going to decode next? Could it master genomic sequences to cure diseases, predict the chaotic sequences of the global stock market? The possibilities are absolutely wild. Thanks so much for joining me for this explainer. Keep feeding your curiosity, and I'll catch you next time.